Hey class, we kind of rushed Newton's universal law of gravitation at the end, and I made a comment that maybe I should make a supplemental video, so I will. I'll leave it to your discretion if you want to watch this, and maybe it'll be helpful. I hope so. But I would say also, though, even though we rushed it, we did cover everything, and so let me start there. Let me start with the idea that if you had one object, let's call it mass little m, and another object, mass capital M, and they are separated from center to center by a distance of r, there is a gravitational force between them that Newton discovered, and we could calculate it this way. And so, as you've heard me say, and I'll say it again, physics is about knowing how to apply a few but powerful concepts to explain a universe of phenomena. So this is that fundamental concept. And so we talked about it. We even gave you the value of g and said, all right, now you could calculate it. And we did calculate 2. And that's as far as we got. So I thought maybe it might be useful to do a few more, because even though we're technically done, it's nice to see a little bit more to it. And so let's look at some work done by Newton that's really added to his purpose of finding the universal law of gravity. And that was satellites. He was trying to figure out, if you will, why the moon does what it does, and why doesn't it crash into the Earth? Now, maybe I should start with a comment about satellites. I think in today's world, when we hear the word satellites, we think of artificial satellite. But in science, a satellite is any smaller object orbiting a bigger object. So then we have natural satellites and we have artificial satellites. So like the moon going around our Earth is a natural satellite. The Earth going around the sun is a natural satellite. But like the International Space Station going around the Earth is an artificial satellite. But they're all satellites and they all work the same way. And that's what Newton was trying to explain. And when he came up with this pattern, he got a deeper explanation. It goes something like this. I'll start with what we already know, projectile motion. And let me start with some kind of object. Newton called it a cannonball, so I'll show you a little video with a cannonball here. But he said, look, if you start 5 meters above the ground and you shoot it in a horizontal direction, it will fall. And we pick the 5 meters because if you put in your 1/2 gt squared with, equals the distance something moved, that would be with an initial velocity of 0 and initial position of 0. So this is our second kinematic equation. You get roughly 5 meters. It actually is 4.9 meters. All right, so it falls 4.9 meters. So this is to say in 1 second, it would travel horizontally because you gave it a horizontal speed and then it crashed it down. Now, if you shot it faster, it would still be in the air for 1 second because the vertical and horizontal components are separate. It would just go further because you gave it a faster horizontal speed. And yet even a faster speed would do the same thing. Now, if you also factor in that the Earth is not flat, that's the big piece right here. And this is Newton's thinking. And so maybe now I'll draw the surface of the Earth with a curve to it. And you start with your object 4.9 or 5 meters above the ground, and you give it a horizontal push. It'll still fall the 5 meters or 4.9 meters in 1 second, but it won't actually hit the ground in 1 second. You would say, well, it didn't hit the ground because the Earth curved below it. Okay, fine, call it what you will. It still won't hit the ground in 1 second. It's going to take a little bit longer. And this is kind of that magical step. Newton realized then if you shot it even faster, so right here, after 1 second, it could be quite a distance still from the Earth. Maybe still 3 meters away from the Earth. And if you really shot it fast, you might actually still be 5 meters away from the Earth. And it just keeps repeating, and it's 5 meters away from the Earth, and it's 5 meters away from the Earth, and it never actually hits the Earth. And maybe drawing from further back, it might look something like this. It would fall, not hit the Earth, still 5 meters away. Fall, not hit the Earth, still 5 meters away. Fall, not hit the Earth, still 5 meters away. Fall, 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 fall. And so Newton's argument was, look, it's not that the moon doesn't have any gravity. It's that it has a sideways motion that is just the appropriate amount that it falls at the same rate it goes horizontally in such a nice pattern that it's never closer to the Earth. And that is the force that is needed to make it turn. We know we need a turning force because it goes in a circle. And so therefore it needs some gravity. But yet it still doesn't hit the Earth. And the force then gives it an acceleration that turns it. It doesn't give it an acceleration that changes its speed. And actually, although we're not in the classroom setting, I want to show you the video from the classroom. Let me take my phone out of its holder and kind of shoot it up here at my screen. Maybe if any of you guys want to watch it, this is the stuff I show you in class. We've got a couple of videos. So there's the web address. But I'm going to look here at what's called Newton's Canon, because this is Newton's argument that, hey, we've got to go really fast. So we got to make a giant cannon. Of course, he does the calculations, and it turns out to be 8,000 meters per second. So Newton realized that although he explained natural satellites, artificial satellites were way out of the technology of the day. But as you know, they eventually, and maybe I shouldn't say they, we, calling us now scientists, made rockets, and now we can get to those high speeds. But let's look at Newton's Canon. It's a neat little video there. And this is the argument, that you fire that cannon horizontally, and it shows a second one dropping, and they hit the ground at the same time. And at 5 meters, it'd be 1 second. But then, take a better picture, which has a curved Earth, and what you'll see, each progressive shot is shot a little faster. And so it takes a little longer to hit. And that one went off the screen. Here's the picture that I really want you to see. The cannon on the top of the Earth, and it just misses, completely misses the Earth. It's continuously falling from the force of gravity, and it just keeps orbiting around. And it has nothing to do with its height being up there, other than for the Earth, because of air resistance, you got to get it high enough, otherwise air resistance slows it down. And so that's really kind of the only reason we put our satellites so high. There's no reason they can't be, in theory, right at the surface of the Earth. All right, well, I hope that video was a little enlightening. Let me put my camera back up here in the holder, and let's keep talking. Let's put this logic into practice. And like I said, I'm not really going to do anything new. That's why I guess I call this a supplemental lecture. But it's nice to kind of put things together. For example, let's do this. Let's pick on a satellite. How about I'll start with an artificial one. Let's do the ISS, the International Space Station. All right. Now, working with the International Space Station, I guess we need to know a little information, and really very little. I will just tell you that it is 400 kilometers above the surface of the Earth, orbiting around. That's it. I won't even tell you the mass. And I'm going to ask this simple question. Could you tell me how fast the International Space Station is moving? All right, well, let's give that a try. So, all right, here is, say, the Earth. Let me call that capital M. And above the Earth, and I'll kind of exaggerate because 400 kilometers would be a lot less than this in terms of the radius of the Earth. But so I can give myself some distance, let me call that little m. All right, and let's say that it is moving around, so it does this perfect circle thing. More on the perfect circle discussion soon in Kepler's first law. But we'll just make it go around here. And my question is, okay, well, how fast does that need to be? To make this orbit work, how fast is it? Okay, well, let's start by pointing out that the universal law of gravity would tell me how much force there is on the International Space Station. I would take the mass of the International Space Station, the mass of the Earth, the distance between them, and this gravitational constant, multiply them together. But also, let's take the beginning half of this chapter. The beginning half of this chapter said, if you add up all the forces, you get MA. Actually, that's chapter 4. Okay, but this chapter then said the A has to be V squared over R. And so I'm trying to point out that if you did a free body diagram on the International Space Station, the only thing tugging on it would be the force of gravity. The force of gravity is its weight. There's nothing else touching it. There's no strings, there's no ropes, there's no cables, there's no chains, there's no table, there's no friction, which means, of course, there's no normal force. We've got it high enough that there's no air resistance. My point is, if I add up all the forces, there's only one. And so this is what we would get by putting the first half and the second half of this chapter together. Now, we might want to pause and say, which m is this? Because we have two of them over here. And, of course, remember, this is the mass of the object going around in the circle. So it would be the same as this little m. So I tried to make them the same symbol, and they will cancel off. And for that matter, the r's will cancel off. And so now you can kind of see what I was getting at here is by a little deductive reasoning, we have an equation for the velocity. I guess actually that's velocity squared. So let me take the square root to get just velocity. So if we know the universal constant, if we know the mass of the Earth, and if we know this radius of orbit, we can then answer this question, what is its speed? Now, I did give you the height above the Earth, so there's a little more information we need here about the Earth to finish this problem, because the radius, and coming back to the picture here, the radius of orbit would be from the center of the Earth. So it would involve the radius of the Earth plus the altitude of it. And that's that 400 kilometers I gave you. Now remember the G back here is in meters. So for the first thing I guess I will do is change the 400 kilometers to 400,000 meters. All right, so in this picture, that's the altitude. What I need to do is add the radius of the Earth, and that's why your author has given you all those in the chapter here, and you can also just Google them. but it is 6.37 million meters. Okay, so that would be adding the two together to get the radius of the orbit. The other thing in that little table here, or somewhere in that chapter, is the mass of the Earth. And it should say 5.98 times 10 to the 24 kilograms. And so there's the numbers. Just to check the units, let me make sure the units work out right. And I'm going to put my units over here and my numbers here. So the units for the G, the gravitational constant, as we said, is a Newton meters squared over kilograms squared. And the unit for the mass of the Earth is kilogram, and then down here is meter. So one of the kilograms and one of the meters cancel off. All right, well, let's keep working. I'll get a number here and then the units. Let me hold off on the number, but if I look at these units, remember a Newton is a kilogram meter over a second squared. So there's the Newton. And if I put it together with this meter and this kilogram, the kilogram will cancel off, and I'll have meters squared over seconds squared. So then when I take the square root, I have meters per second. So again, that's our very useful unit analysis, because it helps us to decide if we've done anything wrong. And we're like, okay, this works out right. All right, so the units match the units I should get, which is what speed is it. So let me now do the numbers. And maybe I'll start with this bottom. So 400, 1, 2, 3. So 400,000 plus 6.37 million meters. So that's the denominator. Let me remember that it's there in my calculator. So let me take the G, 6.67 times 10 to the negative 11. Let me multiply by the 5.98 times 10 to the 24. Now let me divide it by that last answer and hit enter. Now let me take the square root, and this is the number. So the International Space Station needs to be moving at 7,676 meters per second. Of course, that's probably too many significant figures. 3, 3, and ooh, I just rounded that. Let's call it 3. So maybe a better number here is 7,680 meters per second. But point is, we can calculate it. And the point is, it's very fast. And you can see that Newton was able to give an explanation, but not able to design anything, and hence our Newton's canon here. And so now we understand satellite motion, which is why we can make artificial satellites. And we have the technology to go this fast. You can even see in the equation here that if we put it up even higher, it wouldn't have to go nearly as fast. But then we have to get it higher, and that actually is harder to get it higher than to get it faster. So we usually like the near-Earth orbits when we're putting up our own satellites. They're a little bit easier. But there's advantages to those. In fact, what we call the geosync satellites are really nice because you slow it down enough that it would take one day to go all the way around. And since the Earth is spinning and takes one day, that satellite looks like it's stationary above the same spot over the Earth. We like to do that with weather satellites, so they can just sit there and take pictures, and it kind of looks like they're just stationary, but they're not. They're moving. It's that the Earth is spinning along with the movement of the satellite, hence the name geosync satellites. But again, they got to go really slow, so they got to be really, really high. In fact, that kind of begs the question, what is the period? How much time does it take to go all the way around? Now, let me go back to the International Space Station for that, because I would say a very easy way to kind of calculate that would be to say, well, if you've already got the velocity, which we just did right here, and it's going in a circle, you could just say 2 pi r divided by the period, capital T being the time to go around. We could get that time. So it might be fun here to ask, how much time would it take for the International Space Station to go around? If you were a employee or scientist up there at the International Space Station, you know, and you fly over the Earth, you know, say California, you know, and you look down and you go, hey, there's Santa Barbara. I can see the Channel Islands, and all right. And then they're gone because you kept moving. Okay, now, when will I see them again? How much time will it take? And so rearranging this, I would have period equals to 2 pi r over the velocity. So here's the 2 pi. The r, I guess I worked out earlier. I believe that was the number. Let's just go up. Yeah, there's the 400,000. So I'll just put it in as the 6.77 times 10 to the 6, I think. 1, 2, 3, 4, 5, 6. Yeah. In fact, I could just do that in my head. I could see that the 4 would go right there. That's the fifth decimal. All right, 6.77. All right. Guess I don't need a calculator for that. It's amazing how lazy we get when we have calculators. All right, so here is 2 pi and then 6.77 times 10 to the 6. And then divide by this speed. So 7,600, and maybe just to match significant figures, I'll do the 80. And of course, remember, this up here is in meters, and this is in meters per second. So the meters are going to cancel, and so my units here are going to come out to be seconds. All right, so I'll take the 2 and multiply. Oops. I'll take the 2 and multiply by the pi. And then multiply by, and I'll just go up and copy and paste that number. And then divide by the speed. Actually, I'll just copy and paste that number. So, although that's the wrong number of significant figures. Well, I'm going to do it. And I will get the time. So the time, roughly, is 5,542, but I'll stick to my 3 significant figures, seconds. And maybe just for fun, why don't I divide that by 60? And it's about 92 minutes. It's like about 92.4 minutes, which 90 minutes is an hour and a half. So if you look down, you see Santa Barbara, you know that in an hour and a half, you're going to be back over Santa Barbara. You know you're going to see a sunrise and a sunset every 90 minutes. And so it's got to be quite amazing to be up in space and orbiting around. And I guess for $21 million, you too can buy a trip into space and get on the International Space Station. And I guess that's what the Russians do. But I don't have $21 million, so I won't be doing it. But it would be quite amazing and quite fascinating. In fact, let's just do this in symbols. I actually put in the numbers here, but if we put our two thoughts together, this thought for the velocity and this thought for calculating the velocity, which was based on this thought, okay? So that's why I said our deductive reasoning here. This is a supplemental lecture. You really could have figured this out on your own. You could have just said, look, the universal gravitational constant put together with the acceleration of something moving in a circle, solve for velocity, the definition of velocity. You know, that's all I did. So I didn't do anything new here. I just was putting together thoughts from previous chapters. Now, I did it with numbers, but it's kind of nice to do it with symbols. So let me take this, the square root of Gm over R equals this 2 pi R over T. And see, what's nice about this is now I don't have an equation with velocity. And maybe I have something that is more of an observation, that it connects radius and period. And so we can look at the International Space Station. Although, let me switch. Let's look at, say, the moon. Because it's easy for the early scientists to look out at the moon and say, look, the period, we can measure it. It takes 27.32 days to go all the way around. Which, by the way, in passing, if you look on a calendar, it's going to be 29 and a half days, a month. Why the difference? Well, you got to kind of take a look at our whole solar system for that to make sense. If here's the sun, and over here I have the Earth, and orbiting the Earth is our moon. I would say the time for one revolution, and so I'll put the moon over here so it'll look like a full moon. So if I look at a full moon, it goes around, and you go, oh, one orbit will be another full moon. And that should be 27.32 days. But I would say, wait, we got to be careful here. The Earth moves during these 27 days. And so 27 days later, the Earth is here. And the moon, if it goes all the way around in 27 days, is, right here. But that's not directly across from the sun because the Earth moved, and so you don't really have a full moon. If you give it a couple more days, the moon will move to here and be full. And so from your perspective, because you're on a moving Earth, you're not going to see the next full moon for 29 days. And so on a calendar, you'll see full moon to full moon or new moon to new moon. It'd be 29 and a half days. So sometimes it'll be 29 days and sometimes it'll be 30 days, depending on, where the midnight falls on a calendar. So that could be a little misleading, the 29 and a half. An important perspective and where we get our concept of a month. Okay. And it's too bad an even number of months, like 12, don't make a full year. That way we could have months that always have 30 days in it, but that doesn't work either. But the real number I want then is the science number, that the time for one revolution is 27.32, not the calendar days. Yeah, I say that because if I knew then the period, and, of course, the mass of the Earth, I could then figure out the distance to the moon. Or the other way around. And this is actually how they get the mass of the Earth, is to get the distance to the moon and the period of the moon and then calculate the mass of the Earth. But I'm going to do it a little bit differently. I'm going to say, let's pretend we don't know the distance to the moon. Given this information that we've already been given, we can figure it out. All right, so let's give that a try. Now, since I'm not a big fan of square roots, let me square everything. So this becomes GM over R. And, of course, over here, 2 squared is a 4, pi squared, R squared, and period squared. And, in fact, let me just kind of rearrange this. And let me put it in the same order that your textbook does. Your author puts the R's together and on one side of the equation together with the period. And everything else on the far side of this equation. So GM over 4 pi squared. And what's kind of neat about this is Kepler, long before Newton, well, maybe not long before, but a little before Newton, noticed that when you look up at the distances of all the known planets, I believe there were 6 of them at the time, and you look at their period, and you take their distance and you cube it and their period and you square it. I don't know how they decided to do that. He noticed you got a constant number. Now, he didn't really understand why it was a constant number. That's going to take what we're doing. That's going to take Newton to say, well, that constant number would be this gravitational constant times the mass that it's orbiting. And in this case, the orbiting would be the sun, and then over 4 pi squared. So we call this Kepler's third law, because Kepler had 3 quite fascinating observations, and this is the third one. And again, without any knowledge. In fact, I'll just kind of grab your textbook right here and toss it into the screen here and take the information about the sun. And as you look at the Mercury, Venus, Earth, Mars, Jupiter, Saturn, which is all he knew about, and I'm a little baffled why Uranus isn't on here. Huh. Well, Neptune and Pluto. Maybe they say something about it. I'll read this after I get done lecture. But, I am baffled. Okay, anyway, but all of these orbit the sun. And then over here, he gives the radius, he gives the period. But right here, he calculates r cubed over t squared. And he comes out with these number in these units of weird units, kilometers cubed, and the time is in years. But not worrying so much about the units, notice that for the sun, because the sun has a certain mass, they're all the same. And that's what he noticed. Now, there should also be a constant for everything orbiting the Earth, although we only have one moon, so it's hard to compare anything. If you take Jupiter and its 4 biggest moons, you're going to get this same constant, and that's what I'm trying to show here. And so Kepler made a big step towards, or I should say maybe helping Newton get along. That's why Newton said, I stand on the shoulders of giants. And so he looked at a lot of the data, one of them from Kepler, and was able to come up with this universal gravitational, the universal law of gravitation. Okay. Now, like I said, here's what I'm going to do with it. I'm going to try to find this distance. What is the distance to the moon? So putting in the numbers of 6.67 times 10 to the negative 11, putting in the mass that it is orbiting, so the moon is orbiting the Earth, so that's the 5.98 times 10 to the 24. Dividing that by 4 pi squared. Then over here, I would have the distance cubed, so that's what I want to solve for. And then over here, I would have the period. Now, I need to be careful. I didn't put units here, but as we talked about on the other one, this right here is in newtons meters squared over kilograms squared. This is in kilograms. That kilogram and the one that's buried in the newtons would cancel off the kilograms. But my point is the time over here is in seconds, so let me match it over here. Because I told you the time in days. I told you the time was 27.32 days. So let me multiply by 24 hours, then by 60 minutes in an hour, and 60 seconds in a minute. So I could come up with 2.36 times 10 to the 1, 2, 3, 4, 5, 6 seconds for how long does it take in days? All right, since that number is already in my calculator, let me square it and hit enter. And so I've got that number. Imagine moving it to the other side. So that number then would be multiplied by 6.67 times 10 to the negative 11. It would also be multiplied by 5.98 times 10 to the 24. It then would be divided by a 4, and it would be divided by a pi squared. And so all of that should give me the distance in cubed. So then, if I take the cube root of this, I did something terribly wrong. It might have been back here. Ah. Okay. Yeah, back here I forgot to put the times squared in there, didn't I? So this is the 6.67. Yeah, the number I got was just incredibly small, so I'm bothered here. So this is the 6.67 times 10 to the negative 11. This is the 5.98 times 10 to the 24. This is the divide by the 4, and this is divide by the pi squared. Enter. Okay, so that's just this number. What I'm missing is this number. So I thought I was including it, and I forgot to add it. I put it in the calculator. Okay, so let me go times 2.36 times 10 to the 6th squared. Enter. All right, so that should be r cubed. So then let me take the cube root of that. So that'd be like raising it to a power of 1/3. So I will raise it to a power of 1/3. And I get a distance then of 3.83 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 meters. Which, remembering in my head that there is 1,609 meters in a mile, I should get the famous 240,000 miles. 240, yeah, to the moon. Okay, good. So I'm very comfortable with that answer. And good, it worked. Sorry about the mess up on the calculator. But hopefully you see what is Kepler's third law. And it's not so much about Kepler's 3 laws, although your author does at least mention them. So as long as I'm doing a supplemental here, why don't I just mention Kepler's 3 laws? They're the 3 planetary laws. And I just did, really, the third one. In fact, let me grab your book. Your author does it somewhere in here. And it says, oh, well, I guess I was showing you his table for the third law. Okay. But in passing, I will mention his 2 laws and maybe show you the other 2 a video. Kepler noticed that the planet does not orbit in an exact circle. It's an ellipse. And the sun is at one of the focus of the ellipse. And your author does a little here chance of reminding you what an ellipse is. In fact, I will too, but I would even say then a circle is a special case of an ellipse. So I've been doing calculations as if they're circles. The definition of a circle is all the points a given distance, which you would call that the radius, from a center point. So you take a center point, you take all the points equal distance, that's how you get a circle. And so you can see how the early Greeks mentioned circles, and then they said, well, let's do this. What if you had 2 points? What would be all the points equal distance from 2 points? So you got to kind of define what you mean by equal distance, but what it means is if you take the distance between the 2 points and then the distance from each of the points, that the sum of these three is a constant. So this and this is a constant, because we know this distance doesn't change. But what makes it easy to do an ellipse then in a drawing, and this is what your author is trying to show, is if you just pick 2 points and put a string around it, you can then put your pencil in the string and just sketch around it. And so if you were then to sketch around and pick up like a point here, this distance plus that distance, so the distance from this point to the other 2 is the same as this point to these 2. Or over here, this point, if I take the distance to the near focus and the far focus, I get the same number. And so it's all the points that are equal distance from 2 points. So if you imagine these points getting closer and closer together and eventually overlapping, you have 1 point, and so a circle is a special case of an ellipse. And so the further these points get across, the more oblong it is. Well, like I said, I'm just going to skim over this because it's a supplemental. We don't have any homework problems, no test problems, nothing on it. It's just one of the things that you could prove with a lot of rigorous mathematics, and we won't, but using Newton's universal law of gravity. So all of Kepler's laws, sadly, are not really needed. They're all circumseded by Newton's universal law of gravity. And that's why many of us scientists are just like, don't worry about Kepler's 3 laws. We got something better. We got Newton's universal law of gravity. But like I said, it's worth mentioning because really the orbits are elliptical. And unless they're very elliptical, you don't think about it. Because even the Earth looks something like this. Here's the sun, and it is slightly elliptical, where the closest we get is 91 million miles. And the furthest we get is 95 million miles. So you average 93. And that's what most of the time you hear in terms of miles. What's the distance between the Earth and the sun? Oh, it's 93 million miles. But that's the average. It is slightly elliptical. But it's so elliptical that you don't recognize when we're closer, which is in January, and when we're further, 6 months later, July. So I guess we're getting close to that right now. We're getting to the furthest. But it's just not that big of a deal. It's just not that much. Anyways, that's Kepler's first law. The second law, kind of neat too. It just says, all right, so now recognizing that it's elliptical, it actually moves. That is, the satellite actually moves a little faster when you're close to the sun. So if you look at where, say, the Earth is now and maybe 7 days later it's here, it would have swept out an area. But if you do the same 7 days at another location, so start here, and 7 days later it's here, the area here is the same as the area there. And your author gives a good picture of this by saying, okay, when it's close to the sun, it goes fast and it sweeps out area 1. A little bit later, it slows down, so it sweeps out area 2. Even later, it's way over here, it slows way down, and it sweeps out this area. But because it's longer, the area of 1, 2, and 3 are exactly the same. And so he noticed that, and that's kind of neat too, because that actually leads to a principle we're going to get in a couple of chapters called conservation of angular momentum. So again, we don't, as scientists anymore, we don't really think much about Kepler's second law, because Kepler's second law is really the principle of something bigger. And so Newton's universal law of gravity kind of supersedes all of this. And this conservation of angular momentum is a good one. And in fact, on that same web page I showed you, there's a video of Kepler's laws, if you kind of want to see it. Maybe I'll just say, if you want to see it, go click on the one just below Newton's Canon. It's called Kepler's Laws, and it's pretty neat. I won't bother to take time to show it on this, because there's one last thing, and I didn't want the supplemental to be too long. So let's talk about the last interesting thing, and that's tides. And that actually can be a bit tricky for students, and that's what I want to emphasize. I think most students already know that it is the gravitational force of the moon that affects our tides, but it's a bit more complicated than that. It's not just the moon, it's also the sun. In fact, it's any object. And so let's just do something like this for a moment. Let me draw kind of this perfect circular Earth with no continents, no islands, just this blob of water around the whole Earth. Now, the big part of this is to recognize water then flows. Because if you were to put an object nearby, and let me not call it the moon or the sun, but clearly the moon's closer, and you're going to see here the moon's going to play a bigger role than anything else. That's why most people say it's the moon that causes the tides. And it's true, the moon has the biggest effect. But the sun is a pretty significant player, and even, well, and Jupiter's in there, but it's not really significant. And so you can't really completely understand the tides without talking about both the moon and the sun. You can get rid of Jupiter and Saturn and those other big ones. They are kind of negligible. But let's just talk about one object for a moment. And let me write down this equation again. Because again, here is Newton's brilliance. He realizes that this equation is saying the force changes with distance. So if you had this perfectly round Earth and this perfectly then round ocean, you wouldn't have any tides. There's no place where the water is higher than the other. But when you put another object nearby, this object's going to tug on it. And changing colors here, I will say that this object will pull on what I'll call the water that is towards the moon. But it'll also pull on the Earth. And I'm pointing out their difference because notice that the water is flowable. It can move at different rates or a different amount than the solid rock of the Earth. And see, because of that, it pulls the water more than it pulls the Earth. They both get pulled over. The universal law of gravity says they both get pulled, but it also says the stuff that is closer gets pulled more. And so as a result, if I can draw a new picture here, you might say that everything gets pulled over. Yes, the Earth gets pulled over, but the water gets pulled over even more, making a bulge towards this object, which I'll just say the moon. And so I get this bulge towards the moon. Now, it even gets better than that. And this is probably the harder one to understand, is coming back up to this picture, this object, called the moon, if you will, is actually then pulling the water also towards it and pulling it on the back side, but it pulls the Earth more than the water on the back side. And as a result of that, you get another bulge on the back side. And that's one's hard to understand because when you see this bulge, your natural reaction is to think something is pulling the water that way, and there isn't anything. Everything is pulled in my picture to the right, but it's the difference that is important here. This side, the front side, gets pulled the most. The back side that gets pulled the least, and the Earth that's somewhere in between. And so everything gets pulled over, and that's what I'm trying to show with these green arrowheads. But I'm trying to show that the front gets pulled the most, then the Earth gets pulled in the middle, and this back one gets pulled over a little bit less, and the end result is actually an elongated bulge of water and two bulges of water. And like I said, it's a little tricky to kind of comprehend this second bulge. This one's not so bad. You say, well, it got pulled over. Okay, But didn't the Earth get pulled over too? Yeah, but a different amount. So you still get a bulge. And then, of course, it's because the Earth was pulled, it was pulled away from this water. That's why you get the other bulge. Although you can say, well, wasn't that pulled over? Yeah, but not as much. Oh, okay, so the bulge is still there. So this back bulge is here because the Earth gets pulled away from the water. And then this front bulge is here because this water gets pulled over more than the Earth. So there's two bulges. Now, remembering the Earth is spinning, and so in 24 hours, you'll go all the way around, and if you were in this location, it's supposed to be a person, you would be in a place where the water level is low, and you would say, hey, low tide. But 6 hours later, you would now move into this bulge, and you would say, oh, high tide. 6 hours later, you would move to here and go, oh, low tide. And then 6 hours later, you would go, oh, high tide. And then 26 more hours, after a full day, you'd be back where you started. And you'd go, oh, hey, I just had 2 high tides and 2 low tides. And so the best way to understand a tide, or the best way to say it, is the tide is not so much because of the force of gravity. It's because of the differential in the force of gravity. Now, here's why I say that. Because this effect would take place whether this object was the moon or the sun. And granted, the sun is further away, but its mass is huge. And if you calculate m squared over r and compare the force from the sun on the Earth and compare it with the force from the moon on the Earth, you will find that the force from the sun on the Earth is enormously larger, something like 100 to 200 times more. And it kind of makes sense that it would be more because the sun has the biggest influence on us. It's the sun that controls our path. It's the sun that makes us go in a circle. The moon doesn't really control our path. And so the sun has a much greater force. But let me emphasize, tides are not determined by the magnitude of the force. The tides are determined by the differential as these things are pulled away. And the differential is determined by distance. And the reason that's important is the distance from the moon to the Earth, as we just mentioned, is 240,000 miles. But the distance from the sun to the Earth is 93 million miles. And since the tides are determined by the differential between them, the Earth having a diameter of about 8,000 miles, 8,000 miles is a bigger percentage of the shorter distance of the moon than the longer distance of the sun. And hence, the differential between the front and the back of the Earth from the moon is greater than the differential between the front and the back of the Earth caused by the sun. That's worth repeating. The tides are not determined by the amount of force. If they were, the sun would have a bigger effect. They are determined by the differential. And the differential has to do with the difference, the diameter of the Earth, and a percentage of that compared to their distance away. And the moon is closer, hence has a bigger effect on the tides. So, want to just kind of emphasize the cause of the tides and emphasize that it's a differential, not an absolute force. So the absolute force is greatest from the sun, and that's why we orbit the sun. But the differential is greater from the moon, and that's why we say the moon really is the biggest factor controlling our tides. In fact, the author does a really good job by showing you a picture. And I'll look at this picture. And so here is what I was trying to draw. I was trying to draw, here's the Earth, here's the object. The author takes the moon and says, look, you'll get a bulge on both sides. And so this first bulge is because this water is pulled over more than the Earth is pulled over. But this bulge over here is because the Earth is pulled over more than the water on the backside. And as the Earth spins, you would go through the tide. In fact, a terrible phrase that people will say is, oh, the tide's coming in, which I always find funny. I'm not so sure the tide's coming in. We're spinning on the Earth. We're moving into the tide. Likewise, you'll say, hey, the sun moved. It was over to my right this morning. Now it's over to my left. Or the sun went down. The sun is setting. And again, I'm not so sure the sun moved. It's we spun. We moved away from the sun. It's not that the sun moved. We spun away. All right, well, maybe I'm just being anal there. But that really needs to go into our explanation of why then we have 2 high tides and 2 low tides in a given day. Now, what I really wanted you to see in this picture is this one down below, where then the same effects can be done with the sun. And so when you have the sun and the moon in a line, both of them are elongating the water, and they're elongating it in the same direction. And so it really gets oblonged, and that's called a spring tide. And it would be in this place where you have a new moon. See, if you're here on the Earth, the moon would be during the daytime, and you'd see the dark side of the moon. There's no way you would see it during the daylight. So you would think the moon's gone, and then it shows up later. So that's why the early scientists called it a new moon. Oh, wait, there it is. It was gone, and now it's back. Okay, so you would never see this. And so this is what we call a new moon. And anyways, during a new moon, you have really high tides. And because you have really high tides and it sucked all the water, you also have really low tides. And those are always the fun ones down at the beach, where you'll actually see it change dramatically within a 6-hour range. And you can be over here at high tide, like 7 feet, and then 6 hours later, the tide is like -1 foot in our area. And that's the time, you get out there to the tide pools. In fact, just a month ago, we had a -1.8. It was fascinating. So I saw some great set of crabs and stuff in the tide pools. And so I tried to hit the low tide. It worked out perfect. It was a great trip. But anyways, that's a spring tide. Now, when the moon moves, so halfway through the month, so 2 weeks later, it'll be over here. This will be this will be a full moon. Because as we sit on Earth, we can see the full illumination side of the moon. And this, too, is called a spring tide. It's kind of complicated here, but both of them are elongating it. Because remember, there's a bulge on both sides. You might all think that they canceled off, but they don't. If you look here, the moon is elongating it this way, but so is the sun elongating it that way. And so it's not really a cancellation. And so that's why I think your author wants to put here. You'll have a set of high tides and low tides here. So if you have a set of high tides and low tides, 2 weeks later, you'll have another set of high tides and low tides. And of course, you got some effects of nature. This is a full moon. This is a new moon. So this would be dark during the high tide. This is when the grunion run. And so if you ever want to see the fish coming in, they need to come all the way up to lay their eggs, so they need that high tide. But because of predators, they don't want to do it when it's real bright. And so it's this new moon with the high tides that we can make it out to some of our secluded beaches. And if we're lucky, a school of grunion will come up and lay their eggs, knowing then that 2 weeks later, it's going to be another high tide, and the eggs will hatch, and then the little fishies can get back into the ocean, complete their circle of life. All right, that being said, this is the last one I want to say, and then we'll call it quits. This supplemental lecture, oh good, just hitting an hour, is that when the moon is in this position or this position, the author doesn't show it, but we would call this the third quarter because it went 3 quarters around, and then over here would be 1 quarter. So a week after a new moon or a week after a full moon, you will have the two oblong effects from the moon and the sun competing each other. And so you will have the moon trying to elongate it this way, and you will have the sun trying to elongate it this way. And they'll compete with each other. And so what ends up happening is one of them is a little more dominant, and that's what we said the moon would be. So you do get an elongated in this case, a vertical direction, but it's not very elongated. So your high tide is not very high, and that also means your low tide is not very low. So a week after these really high tides, these spring tides, and if, by the way, if the spring tide is coupled with the orbit when the moon, remember this is an ellipse, so if you couple the spring tide when the moon is close to the Earth, you get what they call king tides. And so you get the spring tide at a close point, so you get a lot of tide effects. And so it's those king tides that are the fascinating ones. Like I said, we just kind of passed them. This was the month of April. All right, so back here, this would be boring tides in the sense that, you know, maybe during the high tide, it's 5 feet above sea level, and then it goes to the low tide, which is maybe 3 feet above sea level. So it only changed by 2 feet after 6 hours. It's just not very elongated, and so those are your nep tides. All right, I'll call it quits. Hopefully the supplemental was useful to some of you. Take care.